I think they call this one a rank theorem, but it is pretty darn important theorem. It's fundamental theorem of some finite dimensional vector space, something like that. I'd like to tag it like an importance like that. All right, so here's a rank theorem. T is from arbitrary, abstract vector space and linear maps between abstract vector space, not V to V and V to W like this. And we're looking at the finite dimensional n, and BW is n and m like that. All right, so what about it now? Then we can look at null space and all that. The V is the domain of this map, right? Of T. Do you agree? It's going from V to W, correct? So you remember this null space of T? Null space of T is subspace of what? V. Range of T is a subspace of W, right? So we have subspace inside V, right? So how do we complete this? This is not V, right? It's a part of it. And how do you complete it? Using what kind of symbol? Direct sum, right? This is called basis extension. Null space subspace has its own basis, right? It's probably not enough to cover, and you just extend the basis, and there is this complementary part, V prime. Remember? Is this choice of V prime unique or not? Not unique. There are many different ways to combine with the null space to get everything after the sum. Is this true? Okay. The next thing is that the dimension of this V prime, can somebody imagine, dimension of this V prime is equal to dimension of something that that's true, but there's a better name. That is true. Dimension of V minus dimension of V prime is what this one is, right? But that is not the dimension of something. V minus V prime is not a subspace, right? It's just a subset. So when I write down dimension of something, it better be subspace. What subspace dimension is equal to the dimension of V prime? The answer is rank. I mean, not the rank, range of T. All right? So T is ascending the whole V down to W, right? Some of them dies here, right? Some of them survive. That surviving guys are range, right? And this one is saying the size of how many vectors are surviving in here, exactly the size of that guy you see in the domain. It's a complementary part. All right? So along this range, lots of guys die. Those guys who don't die is predicting the exact dimension of the range T. And from there, you can easily conclude following important formula. This is known as rank theorem. Dimension of V is dimension of null space, right? Because that's a part of this direct sum, plus dimension of V prime, right? But it has a different name, dimension of range T. So that's something you saw in first year linear algebra book. So this is like this. If you have a vector space, a finite dimensional vector space, as boring as the structure ever, you can put it on in a mathematical entity. But whenever you put function on top of it, and then it gets interesting. V coupled with the linear map, and then there's this decomposition associated to it, and that becomes interesting. So with this two notion of vector space, linear map on V to V maybe, then you can still apply this one, not only for P to W, and the dimension splits like this, and there's this nice decomposition of the function like that. So this is called rank theorem. I would like to utilize this last 3 minutes with this example that you already know. So here is an example. T is a map from R4 to R4. always such a map is given by what? Matrix. Thank you. If it is a column vector, God, delete. Okay. If it is a column vector, it is given by matrix, right? So here's a V. So here's my matrix. -3, 0, 9, 3, 3, 3, 0, 0, 1 and -1, -6, -2, 4, 2, -6, -2. Alright, if I give you a full size vector, you multiply, get another one. Alright, so for example, you multiply null space, right? What is this null space of T? Okay, you put it in there, A, B, C, D, or X, Y, Z, W, set equal to 0. And what are you going to do? Right, row reduction. Okay, so here's a row reduction. So that's called M. And here's the row reduced version. 0, 3, -1, -3, -1. And here's 0, 1, 3, 1, and zeros. This is a different matrix, right? M is not equal to N, but is row equivalent. The map you get out of this matrix, map you get out of that matrix is completely different. It's different. It's related. So, but here's the amazing thing is that this ABCD that is a 0 here doesn't change the ABCD to 0 there. That's why you solve the equation. ABCD that is 0 is still ABCD 0 is here. So you can say null space of M is equal to null space of that matrix N. But matrix N and M are different matrix, right? So by looking at this guy here, what is the dimension of this null space? Null space itself is the same. That's amazing. Therefore, dimension is the same, right? So what is the dimension of this null space N by looking at it here? 2, because these are the two non-pivot positions that are appearing in the row, right? They go to free variable of this null space, right? And that's a 2. And this entire thing is a dimension of V, right? There's a 4 dimension. That's the size of this one is a dimension of the input. So remaining columns here, this column here is non-pivot position, a pivot position here, right? And that's a pivot position. Above it is all 0. Seems like they have to do something to do with the rank rest of the part. So here's what it's telling you. This linear relation, do you see that if I multiply this one by -3 and multiply this column by 3 and add them together, you get exactly the third row? You see that? This is a column multiplied by -3. You get the -3. If I multiply by second column by 3, then you get 3. And then add them. So that is -3W1 plus 3W1, W2. And here, this is V1 and V2. You do the same thing, -3V1 and 3V2. Do you think you can see that? That's easy to see here, but here is slightly different. But you can verify that that linear coefficient is preserved here. -3 times 3, that's exactly +9. -3, -9, +3 is exactly 0, right? That coefficient is preserved. So linear relation between the column vector of this M is exactly the same linear relationship with the column vector in here. That's what this row reduction preserved. It preserved null space exactly. That's the amazing part, magic. And another surprising part, linear relationship between the column vectors is the same. The column vector space itself is different, but linear relationship is the same. Those are the two magic things that happens when you row reduce. And that explains these two things is a basis because these two things are generated. Do you see that? 1, 1 will generate everything that is to the right because all low below 0. This tells you these are the bases. These two are the bases. And all you're going to get is a space of these column vectors in this map in here. And this one says you don't have to look at these two. These two will generate the entire range. Therefore, these are the two dimension of range 2. Therefore, dimension of range plus dimension of null space is a dimension of V, the full space, and which is alternative proof for column vector space. Alternative proof of the range theorem of a column vector space. Okay, I'll stop here.